Welcome to my lecture on Chapter 3, Discrete Random Variables. So a random variable is discrete if it has one of these three criteria. Okay. So one criteria is that it could have a finite number of outcomes. A second criteria is that it has the counting numbers as an outcome. So and a third criteria is that it could be what's called countably infinite. And if you're looking for an example, you can look at the geometric series, a geometric distribution. Okay. So let me give you an example here. So here, X is going to be the number of cats in a household. And I'm going to collect the sample size. I'm going to collect data. So sample data. And someone's going to have no cats. That's going to be the first individual I sample. Then I'm going to have someone with one cat. I'm going to have someone with two cats. I'm going to have someone with one cat again. One cat, two cats, three cats, one cat. Another person with two cats. Then two people with three cats. Okay, so here my sample size. Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so my sample size is 11, so I'm one off. So let me delete one of these observations. I had one too many threes. So my sample size is 10. And let's just double check. Great. And now I'm going to make a table. This table is going to be my random variable X versus the frequency. Okay, so the values of my random variable that I observe, notice this is a small sample size, and I'm doing a small sample size simply for the fact that, well, we're doing these calculations on an iPad by hand. And if I needed a larger one, I'd use R. Okay, so the values of my random variable are just 0, 1, 2, and 3. The frequency with which X occurs, that 0 occurred once. There is one individual with no cats. 1 occurred 1, 2, 3, 4 times. So 4 occurred, one cat occurred 4 times. It was sampled 4 times. Then 2, well, 3 people had 2 cats. And 2 people had 1 cat. Okay, 2. Okay, and when I sum all of this up, it gives me the sample size of 10, right? So there's 10. Okay, And then I'm going to form the probability of X occurring based on the sample data. So I think this is going to be 0.1, 0.4, 0.3, and 0.2. So, I mean, they're just taken by the frequency with which it occurred divided by the sample size. And that is a observational probability. Notice when I add these up, they add up to 1. Okay. Now, one other thing that I like to do here is I'd like to note two things. So, P of X is a density function. If it meets two criteria. One is that the probabilities are greater than 0, less than 1. And 2 is that the sum over all outcomes, so minus infinity to infinity of P of X, those add up to 100%. Now, when X is not between 0 or 3, the probabilities are 0, so this minus infinity to infinity still makes sense. Okay. Now, I'm going to go back here and I'm going to erase some of the screen because I need what's written here. So I'm going to erase some things here and I'm going to erase this top part. Okay. And for this new stuff, I'll write in blue. Okay. So one thing that I want to write down is simply the average value. Okay. Now, if I want to compute an average, I think I just take this data. I take 0 plus 1 plus 2 plus 1 plus 1 plus 2 plus sorry, I made a mistake in writing that down. 1 plus 2 plus 1, and that should have been another 1 here. Plus 2 plus 3 plus 1 plus 2 plus 3. And I divide by 10. Okay. When I do that, I'm going to get this number, 1.6 cats per household. Okay. Now I'm going to just rearrange that sum. And if I was to rearrange this, I'm going to group the zeros. Another way of looking at this would be 0 times 0.1 over 10. Then I'm going to group the ones. The ones occurred 1, 2, 3, 4 times. Okay. And I need to remove that 0.1 there. Okay. 4 times this 1/10. Okay. After all, that is 4 ones. Then I have 3 2's, so I'm going to have 3 times 2. After all, that is 2 plus 2 plus 2 divided by 10. Okay. Then I think I'm going to have another 3, but I'm going to have 3 done twice. So I'm going to have 2 times 3 again. And if I was to rewrite this number one last time, I'm going to get this. This is going to be 0 times probability of, this is going to be 0 times probability of 0, great, plus 1 times probability of 1, plus 2 times the probability of 2. After all, the probability of 1 is 1/10, the probability of 2 is going to be 3/10, or 0.3. The probability plus the probability of 3 times the probability of 3. And the probability of 3 is 0.2. That's exactly this quantity right here. So if we look at this piece, it matches this piece. And so does every individual piece here. So the average value is nothing more than this. Is going to be the sum of x times p of x. And that will be the sum from minus infinity to infinity, again, when x is not a value between 1 and 3. P of x is 0. Okay. This is often referred to as the expected value of x. That's e of x. And we calculated this to be 1.6. There's also something called the standard deviation and the variance of x. When you compute what that is, we can do that. It's going to be how far an observation lies from the mean. Okay. I'll switch back to black. So sigma squared, this is referred to as the variance, and that is on average how far an observation lies from the mean or average, and that average is e of x. And remember, there's another keyword, average, here. That keyword average lets us calculate it like this: the average of x minus mu quantity squared. And if we were to FOIL this out, this is going to be this expectation of x squared minus twice mu times x plus mu squared. And now there's going to be a couple of facts of expected values that just come from summations. Okay, so let me just start a new line here. So here's a couple of facts. And then we'll continue the calculation. One is that the expected value of a constant is the constant itself. And the second one is that the expected of a constant times x is equal to the constant times the expected value of x. 3 is that the expected of x plus y is equal to e of x plus e of y. Okay, so now using this fact and going back to the previous page, when we look at this, we're going to see that we are going to take the expectation here of x squared, just applying that third fact, plus the expected value of minus twice mu times x, plus the expected of mu squared. Now we'll remember that mu is a constant, so this boils down to just the expected value of x squared minus twice mu times e of x plus mu squared. And note, mu is e of x. So this just becomes e of x squared minus 2 mu squared plus mu squared. So if I had to calculate variance, that's going to be e of x squared minus mu squared. Okay, and that's often denoted by that symbol. Now, the expected value of x squared, its definition is going to be this. It's going to be the summation from x equals minus infinity to infinity of x squared times p of x. And going back to the data that we have, x can range from 0 to 3. So when that'll be 0 squared times 0.1 plus 1 squared times the probability of 1, which is going to be 0.4 squared. 0.4, not squared. Right, that's what it says. Plus 2 squared times the probability of 2, and the probability of 2 is 0.3. Plus 3 squared times the probability of 0.2. 0.2 is the probability of 3. And so when we do that calculation, we're going to get 3.4. And because this is 0 cat squared, 1 cat squared, 2 cat squareds, our units are cats squared. Okay. So sigma squared is going to be this e of x squared minus mu squared. So that's going to be 3.4 minus this 1.6 squared cats squared. Okay, and that number is going to wind up to be 0.84 cats squared. If I want my unit just to be in cats, I have to take the square root. This is the standard deviation. And a big reason that we do this is because our answer is now going to be in units of just cats, and that is understandable. Now notice when you're doing these calculations, do not round. This is going to be 0.917, and that's just going to be a unit of cats. Okay. Now, let me give you another example, or just something that is important to note, is that your expected value of a function, g of x, this is defined to be the summation from x equals minus infinity to infinity of g of x times p of x. And there's going to be a very important example here, okay? But I want to just go over a few more things, okay? And here's just some facts that are important about variance, okay? So if I have the variance of a constant, that is 0. A constant has no variation in it. It's a straight line. 2 is that if I have the variance of a constant times x, this is going to be that constant squared times this variance. That's the multiply symbol, variance of x. And 3 is that the variance of x plus y is going to be the variance of x plus the variance of y if x and y are independent. Okay, and these are 3 very important facts. You may have to use them on your homework, on your exam, so just take note of them. Okay, now finally, I'd like to go back and just give you an example, or just talk to you about something called the moment generating function. Is called mx of t, and it's defined to be the expected value of e to the t times x. So here I have to recall how to take the expected value of a function, and that function being the e to the t times x. Well, we just noted I have the summation from minus infinity to infinity of e to the t times x times the probability of x. And that is how we calculate the moment generating function. Now, if we go back to our example, data, okay, and our example data being this one right here, this data set right here, that's the example data that we've been using this whole time. Let's calculate the moment generating function, okay? So when x is 0, I'm going to get this expected value. X is going to be 0, so that's e to the 0 times 0.1 plus e to the tx, but x is 1, so that'll be e to the t times 0.4. Plus e to the tx, x is 2, so e to the 2t times 0.3 plus e to the tx, x is 4, so I'll have 3t, so 3 is the next value, okay, times 0.2. Okay, and if I simplify this, well, the only piece that simplifies is just that e to the 0 is 1. So I'll just get that. And that is my moment generating function. Okay. That is the moment generating function. Okay. Now, I could do something curious here, and that would be I'm going to take the derivative. I mean, after all, calculus is the prerequisite for this course, and I'm going to evaluate at 0. Now, when I differentiate 0.1, I'm going to get 0. When I differentiate e to the t, I'm just going to get e to the t times 1. then and let's not plug in 0 yet, but I'll plug in t. Then I'm going to have e to the 2t times 2 times 0.3. Then I'm going to differentiate e to the 3t Okay, its derivative of the inside will be 3 using the chain rule times 0.2. So notice we use the chain rule here. Okay. Okay. So I'll just say chain rule. So already your calculus review has come back and been handy. Now I'm going to plug in 0. When I plug in 0, I'm going to get 0 plus 1 times 0.4 plus I'm going to get 2 times 0.3 plus I'm going to get 3 times 0.2, and that is 1.6. But wait, I've seen that number before. That's the average. So you're telling me that the derivative of the moment generating function at 0 is the expected value. Well, that's going to be a very important fact. Okay. And more generally, the kth derivative of the moment generating function when t is equal to 0 is going to be the expected value of x to the k. Okay. Now, just one more example. If I know the moment generating function, then we know p of x. So i.e., there's a one-to-one correspondence between the moment generating function and the density function. Between moment generating function and p of x. These two are the same. Let me just give you a simple example of why that's true. Okay. So let's suppose that this is our moment generating function is going to be e to the t times 0.2 plus e to the 2t times 0.5 plus e to the 3t times 0.3. And this corresponds to this probability density function, x, p of x. Well, keep in mind there's really a 1 here, so I'm going to have a 1 here. That 2 is the value of x here. This 3 is the value of x here. And if I had to read off the probabilities that correspond to it, 0.3 corresponds to the probability of 3, 0.5 corresponds to the probability of 2, and 0.2 corresponds to the probability of 1. And that is my density function. Okay. Well, that's all for this time. Next time we'll talk about more on discrete random variables. Thank you.